Hello everyone, welcome back to our ETL 512 Electronic Circuit Analysis course. In this video, we will continue with Chapter 3 focusing on the AC analysis of the BJT, specifically the common emitter configuration. I am Puan Asmalia Zanal and I will be guiding you through this lesson. Before we begin, let's look at the COPO mapping for this topic. This lesson maps to Course Outcome 2 and Program Outcome 2. The skills you learn in this lesson will help you connect circuit analysis skills with broader problem solving in engineering. By the end of this subtopic, you should be able to do two things. First, analyze the small signal low frequency response of a single-stage BJT amplifier circuit. Second, calculate the AC parameters of the transistor. To analyze an amplifier in AC, we must first redraw the circuit in AC equivalent form. Here is the step-by-step guide. Step number 1, set all DC sources to 0. Step number 2, replace capacitors with short circuit. Step number 3, remove any bypass elements, if any, introduced by step 1 and step 2. Finally, redraw the circuit. This slide is for example of the common emitter configuration. The circuit and parameters are given and our task is to determine the input impedance, output impedance, voltage gain and current gain. Please take a moment to copy down the circuit and the given values. You can pause the video if you need more time. Once you are ready, let's do this example together. Now, let's solve the example step by step, following the process we learned earlier. Step 1. Set all DC sources to 0. In this circuit, we only have one DC supply, positive VCC. So we remove VCC and replace it with ground. Step 2. Replace all capacitors with short circuits. As we can see, there are three capacitors, Cin, Cout and Ce. Each of them is removed and replaced with a short. Step 3. Remove bypass elements. After step 2, the shorted capacitor at the emitter are in parallel with Re. This means Re is bypassed and can be removed from the AC equivalent circuit. After completing step 1, step 2 and step 3, the circuit looked like this. We are ready for step 4, redrawing the circuit. Let's start by labeling the transistor terminals. In this common emitter configuration, the input is connected to the base, the output is at collector, and the emitter is the ground. Notice that this transistor is NPN type. Start your AC equivalent circuit with the input on the left, the output on the right, and the ground at the bottom. First, let's look at the input part highlighted in pink. At the base terminal, we have two resistors R1 and R2. Consider R1. It is connected between the base and ground. So, in the AC equivalent circuit, we draw R1 between the base to ground. Next, we consider for R2. R2 is also connected between the base and ground. So, we draw R2 the same way. Notice that R1 and R2 now form a parallel connection as both connected between base and ground. You may keep them drawn separately or combine them into a single parallel resistors. Both ways are correct. Now let's move to the output part at the collector terminal highlighted in yellow. Here, there is only RC, which is connected between the collector and ground. So, in the AC circuit, we place RC between collector and ground. Finally, let's check the emitter terminal. For the emitter terminal, there are no other components left, which means the emitter is directly connected to ground reference. Now, the only component left to be drawn is the transistor. For AC analysis, we use the hybrid pi model. Since this is an NPN transistor, here is the model. RBB prime and RPi are in series between base and emitter. GMVpi and RCE are in parallel, connected between collector and emitter. So in the AC equivalent circuit, place RBB prime in series with RPi between base and emitter, then add GMVpi and RCE in parallel between collector and emitter. Finally, don't forget to label the input current IB, the voltage Vpi, and direction of dependent current source GMVpi. Label the input impedance Zin and output impedance Zout. Now, the AC equivalent circuit is complete. Let's move on to the calculation. The question asks us to find input impedance, output impedance, voltage gain, and current gain. But notice that the value of Rpi is not directly given, so we need to calculate it using the formula, where Re is Vt over Ie. Vt is a constant value of 26 mV and Ie is provided in the question. From this, we can determine Rpi. Now we want to calculate the first parameter. To find Zin is looking to the right. Notice that the input and output are separated but share the same ground. So, R1 is parallel with R2 and are in parallel with the series combination of RBB prime and Rpi. After substituting the values, we obtain input impedance Zin equals to 906.17 ohm. The next value to calculate is voltage gain AV. By definition, voltage gain is the ratio of output voltage to input voltage. So, what are the expressions for Vout and Vin? First, Vout can be seen more clearly from this simplified circuit. It is the voltage across the parallel combination of RC and RCE, with the current of negative GMVpi flowing through it. Next, Vin can be obtained by applying KVL around the input loop. With this, the equation is written as shown. Notice that GMVpi can be rewritten as beta IB, which allows the IB terms above and below to cancel out. After substituting the values, the voltage gain is calculated as approximately negative 279.67. The negative sign indicates a 180 phase shift between input and output, which confirms that the common emitter amplifier is an inverting amplifier. The third parameter to determine is output impedance Zout. To calculate Zout, we must set the input voltage to 0, meaning we short circuit the input source. This removes the effect of the input signal so it won't interfere with the output side. With V1 equals to 0 volt, all resistors at the input are bypassed, making Vpi equal to 0 volt. As a result, the dependent current source GMVpi becomes an open circuit. Looking at the AC equivalent circuit from the collector side, we only have RC in parallel with RCE. Therefore, the output impedance is simply Zout equals to 2.7 kilo ohm. Finally, let's determine the current gain AI. By definition, current gain is the ratio of output current to input current. Using Ohm's law, we can express I0 equals to Vout over Zout and In equals to Vin over Zin. This leads to AI equals to AV Zin over Zout. Substituting the values, we obtain AI equals to negative 93.86. In practice, we usually describe the magnitude, so the output current is approximately 94 times the input current. We have reached the end of this topic. We have learned how to redraw a BJT amplifier into its AC equivalent circuit step by step and apply the hybrid pi model to analyze 4 parameters Z-in, Z-out, AV and AI. The example of common emitter configuration provides a high voltage gain. Remember, the output signal is inverted in phase. With more practice, we'll find that this analysis step become natural and easy to follow. That's all for now. Thank you for learning with me, and I look forward to seeing you again in the next lesson. Bye!